Okay, it's time to start the morning session with 3 short talks. Pradeeptha Jain is going to be the first one, and she's going to talk about her PhD research on random walk in Poisson environments of moving traps. Please.
Good morning, everyone. I'm Pradeeptha. I'm a PhD student at ICTS. First of all, I would like to thank the organizers for giving me an opportunity to present my work in this workshop. Today, I'm going to talk about random walk moving in an inhomogeneous Poisson system of moving traps. So let me first give an intuitive description of the model. So first, let's say you consider a one-dimensional lattice. Then at each site, you pay, let's say site Y, you place Poisson nu Y number of traps. So the Poisson means depends on the sites. So that's why we use the term inhomogeneous in the title. These traps, they perform random walk. Now, there's a random walker that starts from 0. As the random walker is moving, it will meet the traps. If the random walker meets any of the traps, it can get killed at some rate. So you can think of it this way. So each of these traps carry an independent exponential clocks. And suppose at some time, the random walker meets 3 of these traps. And if any of the exponential clocks of these traps ring, then the walker gets killed.
Like 3 traps cumulatively, or sorry. So would it be 3 traps cumulatively, or would it be 3 traps at that precise time?
Yeah, at that time.
At that precise time.
Yeah.
No, it's just you wait until the first one rings.
Yeah.
That's it. So it is cumulative, if you want.
So let me describe the model precisely. So let X be a continuous time simple symmetric random walk on ZD with jump rate kappa. So this will be our random walker. And we can model the traps as a collection of independent continuous time simple symmetric random walks on ZD with jump rate 1. I'll denote the number of traps at a site X at time t by psi of t comma x. Now the walk X, as soon as if it meets any of the traps, it is killed at a fixed rate gamma, which lies between 0 and infinity. The gamma equal to infinity case represents the situation when if the walker meets a trap, it gets instantly killed. So if I condition on the trap and trap field, and then also the random walk path, then the probability that the walk survives up to time t is just the probability that all these exponential clocks of the traps that the walk encounters on its way doesn't tick. Now, if I average over the walk, we get something called the quenched survival probability. And if we further average over the field of traps, we get the annealed survival probability. So in this talk, I only talk about the annealed survival probability. And if I say survival probability, I mean the annealed survival probability. So the question of interest is, we'd like to know how this Z gamma t behaves as time t tends to infinity. So let me briefly give some literature on this topic. So if we consider the homogeneous setting, that is nu I equal to nu. I place IID posts on new traps at each site initially. So, and if the traps are immobile, then Donsker and Varadan showed that the survival probability up to time t behaves it decays exponential to the power some constant times t to the power d by d plus 2. I'll give you some intuition in dimension 1. So suppose you fix a radius r naught, and then you say at time t equal to 0, I don't place any traps in this ball of radius r naught. This can happen with probability e to the power minus nu times 2 r naught plus 1. This is just that the Poisson random variable takes the value at each of these sites. And then you restrict the walker to stay within this ball of radius r naught. And by Donsker's invariance, we can lower bound this by exponential c times t by r naught square. Now you optimize over r naught, and you'll get this lower bound. So in one dimension, it is e to the power minus c times t over 1/3. So you can also get a matching upper bound, and you get this result. So now in the same setting, homogeneous case, but now the traps are moving. In this case, Drevitz, Gartner, Ramirez, and Son in 2012, they showed that in dimension 1 and 2, the annealed survival probability, it decays sub-exponentially. So in dimension 1, it's like exponential to the power minus c times t over half, t to the power half. And in dimension 2, it's like exponential minus t over log t. And in dimension 3 and above, it decays exponentially. So I want to point out some observations in the homogeneous case. So at time t equal to 0, you place IID Poisson new traps at each of the sites, and then you let these traps to perform random walk. As it evolves, if you look at any site at any time, the distribution of the number of traps, it remains IID Poisson with the same mean. And this trap field is also reversible in the sense that if you look at the evolution of the traps from 0 to some time capital T, it has the same law as the evolution of the traps going from capital time T to 0. There's some sort of time reversibility. And using this reversibility, you can make some connections to the parabolic Anderson model. It's a heat equation with a random potential. And they show the subadditivity of minus log of z gamma t. And this will be used to prove the existence of this annealed Lyapunov exponent here. So instead of the constant nu I, what if I place some general nu I, some function nu I? So do we get the same decay rates? Let's look at one example. Let's say I take nu I to be nu if y is -1 and 0 otherwise. So I'll only place Poisson new number of traps at -1, and I don't place any traps anywhere else. So in this case, it could happen with probability e to the power minus nu that I don't place any traps at all. So in that case, the walker will definitely survive. So we can lower bound the annealed survival probability with this event, and this doesn't decay with time. So we might not get the same decay rates as the homogeneous case. You can also think of maybe at all these blue sites, I'll place Poisson new 1 number of traps, and at all these LO sites, I'll place Poisson nu2 number of traps. And I want to know what kind of decay rates I would get for the survival probability. I'll try to answer this question in the later part of the talk. So I want to briefly remark on the properties of the trap field in the inhomogeneous case. Now, if I start with the Poisson nu y number of traps at site y initially, then and I let it evolve, then the number of traps at a site x at time t is it remains Poisson distributed, but with mean this term. And the trap field xi is not reversible in this case. And therefore, we cannot map it to the parabolic Anderson model, or we cannot, and it's difficult to show subadditivity of this minus log of z gamma t. And therefore, we cannot, it's difficult to show the existence of Lyapunov exponent in dimension greater than 3. So we will need new techniques, and we also want to make some assumptions on nu y. Recall that xi t comma x is the number of traps at site x at time t. So the first assumption is that these nu y's are uniformly bounded from above. And the second assumption is that the time average of the mean number of traps at the origin, it goes to a limit lambda as t tends to infinity. My third assumption will be that if I look at the average number of traps, then I want the average number of traps at 0 to be minimum. If all these three assumptions hold, then we have the annealed survival probability will have this asymptotics. And we have the same decay rates as the homogeneous case. So now, if I consider the homogeneous setting where nu y is nu, that case will satisfy all these three assumptions. And in the homogeneous case, this lambda will be nu, and we'll get back the homogeneous result. I want to give some examples of configurations that will satisfy the previous result. This is the example that I mentioned before. I place Poisson nu1 traps at blue sites and Poisson nu2 traps at yellow sites. In this case, this is uniformly bounded. And if we look at this assumption, this configuration will satisfy that assumption with lambda equal to nu1 plus nu2 by 2. So, and in order to satisfy the third assumption, let's say we assume nu1 is less than nu2. Then we get this asymptotics. So consider the second example. If I take this trap configuration, the average trap configuration, which looks like this, then this is less than C. So it's uniformly bounded from above. And lambda will be equal to C. And we have this asymptotics. So intuitively, we can think of it like, even though you start from, on average, you start from an inhomogeneous setting, on average, the traps will try, because they are performing random walks, they'll start to homogenize in some sense. They'll average out, and that's the main contribution to the asymptotics.
Sorry, can I ask a question? When you were in the homogeneous case, Sorry. When you were in the homogeneous case, there was no dependence on the nu in dimensions 1 and 2? So there was a nu there. So now you basically just replace this by its mean. And this condition, the third condition that you have, somehow wants to say that you pick your nus in such a way that there are more traps outside, far away than close by.
Yeah.
Okay, good.
Yeah. So now I'll give a quick outline of the proof strategy. So first, for the lower bound, we'll follow the similar procedure as the immobile trap case. You first fix a radius RT. Then you say at time 0, I don't want to place any traps in this ball of radius RT. And I want to say, I want the walk to be confined in this ball of radius RT until time t. And now we have to, since the traps are moving, we need to put an additional event that no traps that are outside this ball of radius RT enter this ball of radius RT. Yeah. So all these three events are independent of each other. And if all these three events happen, the walker will definitely survive. So we can lower bound the annealed survival probability with this. Now, we can compute these, estimate these probabilities like before. And using the assumptions, we can also estimate this probability. And we get this expression. And now we have to optimize over RT, and this term will dominate, and we get the asymptotic, the lower bound asymptotics for the annealed survival probability. Now to upper bound, we'll recall this assumption that on average I want minimum number of traps at 0 at all times. This will imply that average over the field of traps, the probability that the walker survives is maximum if the walker stays at origin and doesn't move at all. So out of all the random the paths the walker can take, the best strategy for the walker is to stay at origin and not move. So this result for the homogeneous case was proved by Morrow, O'Shannon, Banichou, Copin in the discrete time setting in 2003 and 2004. And they named it the Pascal principle because Pascal once said that all of humanity's troubles stem from man's inability to stay quietly in a room. So, and the result in continuous time was given by Drevitz, Gartner, Ramirez, and Son in 2012. So now, if we use this Pascal principle, we can upper bound the annealed survival probability by this red term here, which is the survival probability of the random walker until time t if the walker doesn't move at all. So now we are left to estimate this one. So there's a paper by Cox and Griffith where they show large deviation results for the homogeneous Poisson system of particles. And we can borrow some techniques from there to estimate this quantity. So first, you average out the Poisson field, and you get this. Now, this summation in the inside the exponential, we can write it as a series for some suitable choice of phi n's. And we can also get a recursion relation for these phi n's, and thus a recursion relation for this summation. Now you can use Laplace transform and Tauberian theorems to obtain this asymptotics. And thus we can upper bound the anneal survival probability with this. Note that the decay rate. Oh, it's the, yeah, it's the river. Sorry, it's the river. So the decay rates in the for the lower from the lower bound and upper bounds match, and we get the result. So we can do the similar calculation for dimension 2 as well. I want to give some remarks. So the problem, it still remains open for dimension 3 and above. So we cannot, there's no subadditivity or no connection to parabolic Anderson model. So we cannot show the existence of the Lyapunov exponent. The assumption 2, which is a time average, we can weaken this assumption by scaling the time with an alpha here, and also including a slowly varying function as t tends to infinity here. And there are also example configurations for which the Pascal principle does not hold. For example, if I place traps, Poisson new traps at 0 and don't place any traps in other places, then this staying at 0 is not a good strategy. If the walker has better chances of survival if it moves away from origin. So in these kind of scenarios, the upper bound argument will not work, and this, it still remains open. As I mentioned this Cox and Griffith paper on the large deviations for the homogeneous Poisson system of traps. So we can get similar results for the inhomogeneous setting. So if I denote the number of traps which visit the origin up to time t as dt, and then under the assumption 1 that the new i's are uniformly bounded, and assumption a2 dash, which is this assumption, we can show a law of large numbers results, central limit theorem, and also large deviation results in the inhomogeneous.
And what was alpha in your previous slide? Oh, yeah.
Yeah, that. So these are the references. Thank you.
Thank you. Questions?
So like continuing from the question that I had asked earlier, right? So in this case, it's like, the person dies when, a given number of traps rings for him up to like this time t, right? So like, what if we like tweak the model to like, precisely a given number, let's say like n traps have to ring for him at a precise time t. So for example, if anything less than, let's say n traps like rings at like a previous time, it basically like the counter like resets, right? So I was wondering like, do you have any ideas as to how that would like, tweak the bounds, or like could the same techniques be used to analyze that scenario as well?
Sorry, I did not get.
So it's basically like a threshold model, right? That you need more traps at once to trigger off the death of the walker. It's not triggered by 1, but you need to wait until 3 do this.
So like, you could think of the traps as like kind of like the degree of an injury that somebody suffers, right? If somebody just has 1 trap, maybe it's just like a minor injury, and then at a later time he's like recovered. But then even if it's like 3 traps, that's like a fatal injury, and then they die.
Yeah, I think.
Difficult. Yeah.
Yeah.
So in the last remarks, in the d equal to 1 case, you said alpha is between half and 1. What goes wrong if alpha is less than half?
So if you consider this case, because the mean number of traps at a given site is given by this expression. And if I just take only traps at only one site, this probability kernel will behave like 1 over root t.
Okay.
So you can say it can't be less than 1 over root t in some sense, in dimension 1.
All right. Okay.
So is the following intuition correct? You said for your lower bound, the hardest thing was to keep the traps entering a large interval. And in the end, for your upper bound, you prevent them from entering the origin. And these probabilities are more or less the same.
Yeah.
Is that correct? Or, well, asymptotically the same?
Yeah.
Because you, in order to stay away from a single site, that's a bit like staying outside of an interval. Of course, your news are somewhat different, but your asymptotics would be that they're sort of comparable for large news. Is that the correct intuition why the upper and lower bound match?
Yeah, even in the lower bound case, this estimate, this will involve this the survival probability that the walker stays at origin. You can this.
Yeah, you said that that's winning,
Yeah.
and that all came from not entering a big
Yeah,
interval, and that's more or less the same as not
Yeah,
entering the origin.
Right.
And because that gives you upper
Yeah,
bound,
yeah.
right? So that's a fair picture then. Okay. Okay. Thank you, Pradeeptha.